Okay, good afternoon, everybody. Welcome. Sorry for the slow start with our AV difficulties on the first of the fall colloquium series in the digital transformation colloquium. You know, a little bit by way of the Institute, it's presenter mode. Okay. So the mission of our institute is to attract the world's leading scientists to join in a coordinated and innovative effort to advance digital transformation of business, government, and society. The group of partners is led by Berkeley in Illinois and has CMU, the Royal Institute of Technology, Stockholm, MIT, Princeton, Stanford, the Berkeley Lab, Lawrence Berkeley Labs, and the National Center for Supercomputing. The consortium is largely funded by C3.ai and Microsoft. Additional support is provided by AstraZeneca, Baker Hughes, and Shell. This is our schedule of the fall. We took a little bit of a hiatus over the summer, and actually we restarted last week. And here are the speakers. Deborah Shaw from MIT next week, Yishai Menake from Cloud Research, Murat Archak, John Doyle, Sanjay Shakotai, and Wei Liu, and Kayu Guan. So these are the speakers, and there'll be more speakers in the month of November that will get filled out. We also, through the Institute, have a number of workshops. The very next workshop is on networks of machine learning, for machine learning, by machine learning. It's really about the impact of new wireless technologies on machine learning. And October 26th and 28th is about how buildings in the built environment are being transformed. And this is going to be one of the biggest sources of energy consumption in most economies. The talks are repositoried on the YouTube website that is displayed up there, and we are a little slow, but it's a great pleasure to introduce Ben Van Roy, professor at Stanford and a dear friend. The title of his talk is Reinforcement Learning Bit by Bit. Ben has been a professor at Stanford since 1998, perhaps 1998, and he has really been working on reinforcement learning for quite some time. Beyond academia, he works with the DeepMind research team in Mountain View, but he has also been involved in a number of startup activities. He has had several really important awards, including the George Newton undergraduate award at MIT, the Master's Thesis Award, the Morris Levin Master's Thesis Award, and the George Fowles Doctoral Dissertation Award, the NSF Career Award, and he, as you will see when you listen to him speak, he's a fantastic expositor, and it's indeed a great pleasure to have you, Ben, talk about a subject that is on everybody's minds. So without further ado, I apologize to everybody for the delay, but we're very glad to have you, and let me turn the floor over to Ben. Thank you.
Thank you for the kind introduction, Shankar. It's great to see you again. It's been too long, and looking forward to talking more and hearing what people have to say about the topic of reinforcement learning today. Shall I share my screen at this point?
Yeah. Please do. Yeah. And someone's going to mute me and turn me off and all that. Yeah.
Okay, so how's that work?
Yeah, it looks great.
Thank you. All right, so I'm going to talk about this topic of reinforcement learning bit by bit, really an overview of some content from a paper that I recently wrote with a set of collaborators listed here. It's a bit of a long paper. I think it's 75 pages at this point. And so I'm not going to be able to cover everything in the paper, but I wanted to share with you some of the key ideas and some of the perspective that we developed as we worked on this topic. So reinforcement learning has attained notable success, but that success has predominantly involved simulated environments where you can simulate for a very long time and throw a lot of compute to generate a lot of data to learn from. And a pressing question in the field at this point is how to extend this success to real environments where you have to economize on data. And the real obstacle here is to address the data efficiency of reinforcement learning agents that are currently considered state of the art. And this was a cartoon plot generated by a friend of mine, Martin Riedmiller, who's a roboticist, illustrating his experience with state-of-the-art reinforcement learning agents applied to a simple robotics task that only involves stacking a few bricks. And the idea there is you have to simulate an agent for a very long time in order for it to generate even rudimentary competence at such a task. And we're talking about years of real-time learning that would have to take place even for a robot to learn how to stack blocks. Okay, so this is meant to illustrate the fact that we have a long way to go to develop agents that can learn from real-time interactions in a reasonably efficient manner. Now, just to offer an example here, one agent that is well studied in the reinforcement learning literature is the DQN agent. And if you apply that agent even to a very simple task of trying to balance a pole by pushing a cart left and right on a track, if you reward the agent with a sparse reward structure where you only tell the agent it's done a good job after the agent has the pole perfectly balanced and centered. If you apply DQN agent to a problem like this, essentially never learns to complete the task. After about an hour of learning, this is what the agent ends up doing. After 5 hours and after 10 hours, the agent has basically learned to do nothing because there's a bit of a cost it incurs for consuming energy, and it's never gotten a reward, and it's basically doesn't want to do anything anymore. Now, the good news is simple modifications to such an agent can actually lead to one that does very well on this particular task. And here's an information-seeking variation of the agent that we've tried. After an hour, you get something like this. After 5 hours, you get something like this. It's starting to figure out that sometimes it can get a reward. And after 10 hours, it's essentially perfected its ability to perform the task. So the upshot here is that while state-of-the-art agents are sort of hopeless in terms of data efficiency in many cases, I think there's a lot of room for improvement in many directions we can take to improve their data efficiency. Now, I think this is a really important obstacle to overcome because many important technologies can benefit from data efficient reinforcement learning. And just to offer one example, the whole area of getting AI agents to learn from human feedback is one that can really be addressed using reinforcement learning if we were to overcome this data efficiency issue. And so there's many applications already that leverage learning from human feedback in language modeling, image classification, product design, robotics, right? And as these applications become more sophisticated, as we want to get more nuanced feedback from humans and have more interactive processes for feedback from humans, the technology is not really there to do that, and data efficient RL could be the solution here. Just to share how I could imagine a data efficient RL agent playing a role in this world. You have a center which is trying to learn something. You have crowd compute technology, which manages relationships with many people across the internet. And you can imagine a data efficient reinforcement learning taking the role of designing and issuing queries to crowd compute technology and interpreting the responses it gets back from the crowd, and trying to do this in an efficient way to make good use of people's time. It's worth mentioning that I also think this could be a direction for addressing one of the what I consider to be a big problem with artificial intelligence. Some people call this the reward alignment problem, and human feedback could address this. But the issue is that AI as a means to solving many of our problems could be on a collision course. The state of the art of AI is one in which we have many sophisticated algorithms for maximizing reward functions, and a limitation that keeps coming up is that we have to specify these reward functions, and misspecified rewards induce bad outcomes. There's many stories about this, like for example, Amazon tried to automate using AI their system for screening applicants for interviews in the company, and they found that the system quickly converged on only interviewing white males. Or Microsoft had a chat bot that was trying to entertain counterparties over the internet, and it quickly converged on a mode where it was spewing offensive rants to people. And so there's all these situations where the AI is sort of doing a good job at maximizing some kind of objective, but the objective is not perfectly specified, and the AI learns how to game the objective and ends up leading to really undesirable outcomes. Okay, so I think the main issue that we need to address here is that rewards ought to align with societal values, and we need a system for accomplishing that. And in order to do that, AI needs to efficiently learn from humans, and the kind of reinforcement learning system that I mentioned could play that role if we overcome this data efficiency issue. All right. So with that motivation, let me talk a bit about data efficiency in RL. And the way I see it, data efficiency in RL is really driven by three issues. An agent needs to think about what information it ought to seek, how to seek that information, and given the observations that it's registering, what information to retain from those observations. All right. And so what I have in mind here is an agent that is interacting with an unknown environment, at each time taking an action AT, and then registering an observation OT plus 1. And to be efficient in its interactions, it really has to do a good job of reasoning about these questions. All right, so I'll talk today about some work that is oriented towards thinking through these questions. And I'll start with some inspiration that offers motivation for our approach and motivation for hope for what may be possible in this area. Then I'll talk about some reinforcement learning agents, and then the role of uncertainty in agent design, and finally the role of information in agent design. All right, so our inspiration comes partly from the field of communication, which has had to grapple with data efficiency for a long time and has done so quite successfully. Now, in communication, we take observations and encode them and pass them through a channel, then decode and try to reconstruct the observation. And the goal in communication is typically to maximize the number of bits per second that you get through a channel. The picture in reinforcement learning is a bit different, but still it's interesting to relate these frameworks. In reinforcement learning, we have an agent applying what I call an agent policy, pi agent. And at each time that policy applies an action to an unknown environment and then registers an observation. And the goal of the agent is to maximize reward. Now, a difference from communication is that in reinforcement learning, bits of information are a means, not an ends. Right? The end goal is to maximize reward, not to gain information. And because of that, while the concept of information is useful to think about here, you need some kind of extra concept that helps translate between information and reward, and some notion of cost per bit needs to come into the picture in order to think about the role of information in reinforcement learning. All right, now, it's interesting to think about the history of communication and contrast that against the history of reinforcement learning. Now, in the 1900s, communication was already a hot topic. That's Marconi there, and the focus of research in the early 1900s was on power generation and how to amp up the power in order to send signals over longer distances. And the way these signals were designed and transmitted was somewhat heuristic. And then in the 1940s, led by Shannon, there was this effort to formalize communication, and out of that came concepts like the concept of a bit and concepts about what the fundamental limits are of communication. And the way I see it, a lot of this effort was guided by Shannon's maxim of information first, then computation. The idea being there was an effort to think about what one could do if there were an infinite number of computation, an infinite amount of computation possible. So sort of like not worrying about computation, what's possible. That was sort of the guiding approach to thinking about communication at the time. And indeed, a lot of theory came out of that that helped to clarify what's possible, but not as much useful, practically implementable technology. It was later, like in the 1960s, when people started to were able to design practical encoders and decoders that could achieve these fundamental limits. And that was really where computation came in, and people started thinking about how to do the computation right. And really practical implementations came in the 1990s. And this paved the way for the connected world where we find ourselves in today. Okay, so that's sort of one view of the history of communication. And when I think about the history of reinforcement learning, it sort of followed a different path, and part of this was guided by Rich Sutton, but also others like Klopp and Andy Bartow and others. But the maxim was sort of implicit in the way they think, was a maxim of computation first, then information. And the way these folks think is that, you know, the tough part is to come up with useful computational tricks that can be implemented and simulated. And, you know, information is sort of something in the back of their minds, but not really the gating factor. So with this maxim of computation first, then information, in the 1990s, there was a lot of work on heuristic algorithms for reinforcement learning. And then in the 2000s, around 2010 or so, you know, with the advent of cloud compute and, you know, the increasing availability of compute power, there was a lot of effort to continue tinkering with these algorithms and to scale up, addressing more complex simulators and throwing more computation at these algorithmic ideas and experimenting to innovate on that front. Now, a lot of success came out of that in terms of very impressive simulation results and strategies for things you can simulate, like board games. But we've got a ways to go to get to real-time reinforcement learning that is data efficient, and perhaps it's time now to carefully quantify and optimize how information is used in reinforcement learning. All right, so let me talk a bit now about reinforcement learning agents. All right, so when I think about agent design, you know, we're designing the agent to plug into a particular interface. And the interface is defined by a set of actions and a set of possible observations. And the way I frame agent design is at any time the agent has seen a history of actions and observations. And there's an environment it's interacting with. The environment is defined by primitives, including the interface, script A and script O, identify the set of actions and set of observations. And then there's this row, which is provides observation probabilities. So for each history and action, the environment generates a next observation based on these probabilities. Now, these probabilities are not known. Right? That's why this is a learning problem. The agent does not know what row is. And over time, presumably learns about that and learns to behave more effectively. I should mention that I've been working with this formalism over the past number of years, partly in an effort to stop pretending that the environment is a Markov decision process. A lot of the reinforcement learning literature frames environments as Markov decision processes, but you know, if we really want to design practical agents, we should get away from such a restrictive assumption about the environment. Okay, and the framework I have here, I think, is fully general. Well, here's an example of an environment, and you could design an agent to work in this environment. You could have an agent that interacts with a computer terminal and does things through the terminal, perhaps through that interacting with the World Wide Web at large. But in this case, you know, each action could be a keyboard stroke or mouse click or mouse movement, and the agent could be registering as observations pixels from the image rendered on the screen. All right, so to think about this design problem, it's useful to define a few foundational concepts. One is a policy. What's a policy? A policy generates, assigns probabilities to actions as a function of history, right? And so policy pi is just a probability distribution over actions given the history. And the probability with which the agent selects any particular action, AT, if it uses policy pi, is given by the probability, is given by that policy. Then there's a reward function. Okay, so reward function is a way of specifying preferences of the designer. And we'll think of reward here as being a function of history. So capital RT plus 1 is the reward realized at that time. And that's some function of history that the designer has to specify in order to design his agent. And then there's a notion of a policy value. For any policy pi, there's a value v bar pi. And I'll define that to be the expected sum of rewards over some long horizon. So v bar pi is a random variable because it depends on the environment, which is a random variable. We don't know what the environment is initially, and so v bar pi is what the expected sum of rewards would be conditioned on the environment. Okay, and then there's some optimal value for the environment. That's v bar star. Okay, and hopefully, over time, the agent can learn to operate about as well as a policy that would generate v bar star. All right, so that, and with those concepts in the background, we can start to talk about an objective for agent design. Agent design amounts to designing a particular policy. We'll call that the agent policy, pi agent. And it's the policy that the agent will use to select actions. And one possible objective is regret, which I'll define regret over some long time horizon, capital T. Okay, and we might want to choose a policy pi that minimizes regret. And I'll define regret as the expected difference between the optimal value v bar star and the value v bar pi realized by policy pi. And we could frame the problem as wanting to design an agent, pi agent, that minimizes this notion of regret. But this kind of definition, which actually comes up in what's called the Bayesian reinforcement learning literature, hasn't been very fruitful because the kinds of agents that people actually design rely on all sorts of computational tricks, and it's hard to think about those tricks and how to improve them through this very abstract framework. And so it'd be nice to offer a more interpretable objective that helps us get our minds around the particular design tricks that agent designers use today, and can lead to ways of improving them to attain data efficiency. All right, so what to do? Okay, so before I talk about what to do in terms of objective, let me give an example of one of these agents. This is this DQN agent, which was made famous by DeepMind. It was designed for the arcade game interface. Right? The agent, the actions control a joystick and the joystick button, and the observations are pixels from rendered in the image for the computer game. And the interesting thing about the DQN agent that made it famous was it attained above human level performance in most video games. And at a high level, the DQN agent tunes a neural network as it learns. And the neural network maps recent frames from the video game to estimates of action value. So theta t here represents the weights of a neural network, and q theta t is the function represented by the neural network. It's a function of state and action. And so in DQN, it's not really a state. It's ST is like a bunch of recent frames. We put in the recent frames as input to the neural network, and it outputs one value per action, which is represented here by this q theta t st dot. The dot is what you'd fill in with an action. And then, so DQN learns a structure like this, tuning theta t over time to adapt the neural network. And what DQN does is at each time, it selects the next action to maximize these action values q theta t, but it applies its epsilon greedy exploration to that. So with some probability of 1 minus epsilon, it chooses the action that maximizes its value estimate. And with probability epsilon, it chooses some other action uniformly at random. All right, one other element, in DQN is a replay buffer. DQN stores a bunch of recent data in order to query that in the neural network training that it's doing over time. It doesn't only train on one sample and then throw that away. It keeps lots of samples in a replay buffer and constantly is training the neural network using its samples. And it has some strategy for deciding on what data to keep around, what data to eject. But effectively, it keeps around recent data and ejects old data. Yeah. That's a high-level description of DQN. Now, when you look at an agent like that, as well as just about any other current state-of-the-art agent, there's some important missing ingredients which are essential for data efficiency. One is an agent, in order to be data efficient, ought to represent what it knows and what it doesn't know, right? And the reason for that is obvious. Like, if it knows about something, it shouldn't gather more data about that. If it doesn't know about something, and that something could play an important role in what it wants to accomplish, then it should go out and collect data about that, right? So an agent like DQN is just managing a point prediction of what the value is going to be in the future. It has no notion of how certain or uncertain it is about various values in various contexts. Okay, so clearly there's a big piece missing there. The agent doesn't do anything intelligent in deciding what to learn, right? The agent's exploring by taking epsilon greedy actions and just sort of choosing actions at random when in order to make sure it's going to learn something new, right? That seems pretty silly. The agent should be more strategic about deciding what it is that it wants to go out and learn about. Sorry, that was my third point. The agent should be strategic in choosing actions that lead to the right information. What I meant by deciding what to learn is the agent may not want to learn about everything, right? It may want to focus on learning about things that will allow it to improve its rewards, right? It doesn't want to learn information that's not actionable. It doesn't want to learn ways of improving reward that require too much time and effort and too many bits of information, because that might not be worth the investment. Okay, so deciding what to learn is important, and then choosing actions to seek that information is important. Finally, the way it retains information is important, right? DQN is retaining a buffer and throwing away old data. That's too simplistic. The agent needs to be more strategic about what it retains from observations, right? Beyond that, algorithms like DQN, as well as all state-of-the-art agents, shockingly, only learn from rewards. So essentially, when something like DQN is training these neural network weights, it's adapting them in response to rewards. Right? That's mind-boggling because the observations are much richer. You're seeing pixelated images. There's so much information there beyond whether you're getting points in a game or not. And the agent is not really trying to learn from that. It's just trying to calibrate to rewards. Okay, so it's just missing out on huge opportunities there as well. And so when you look at these bullet points, it's sort of obvious that there's just enormous room for improvement in terms of data efficiency. But to address these challenges, we need to be able to represent and reason about uncertainty and information in a more intelligent way. Okay, so that leads me to the next topic, which is the role of uncertainty in all of this and how one might go about doing a better job at tracking and representing uncertainty. Okay, so first of all, when we talk about uncertainty in reinforcement learning, there's really three sorts of uncertainty that I'd like to classify, bin things into. One is algorithmic uncertainty, right? So algorithmic uncertainty is the randomness that the agent itself may inject in the way it chooses actions as a function of history. There's aleatoric uncertainty, which is if we knew everything we could possibly learn about the environment, right, there still may be uncertain outcomes. These are the so-called roulette lotteries in an environment, right? They're outcomes that are random, even if we knew all the physics of the environment. And finally, there's epistemic uncertainty, which is uncertainty about the environment itself, right? This is what the agent might want to learn about. This is the so-called horse race lottery, right? Where the agent doesn't know which horse is better or worse, and by gathering more information, maybe it'll figure that out. So learning in reinforcement learning represents the reduction of epistemic uncertainty, right? The agent's not going to be able to reduce other sorts of uncertainty, or that there's nothing to learn about there, at least. But it's the epistemic uncertainty that the agent is reducing through learning. All right, so one technology that my collaborators and I have been developing, and we plan to open source some code on this soon, is this topic of epistemic neural networks. And the idea with epistemic neural networks is, the epistemic neural network is really an interface for algorithms that represent and adapt epistemic uncertainty. And the spirit here is to represent epistemic uncertainty as a distribution of functions, right? And there's actually a whole field that has already been doing this, but it's been hard to organize this topic and compare approaches and improve on the state of the art of the technology, because there hasn't been a uniform interface. And so examples of work in this area would be, neural network ensembles, so-called deep ensembles, Bayes by backprop, prior networks, hypermodels, et cetera. So there's a whole corpus of knowledge here. And what my collaborators and I have done is we've created a library of these things and a test bed with synthetic and real data that compares all these things clearly. And we also have some technology that improves on all of this. And so stay tuned, but we'll be putting out soon tools for working with epistemic neural networks. Okay, but the spirit of this is, if you look at something like DQN, right, it's storing a neural network that maps some proxy for a state, like the last few frames, to a prediction of value, right? And the weights of the neural network parameterize that function. Well, in an epistemic neural network, the way to think about this interface is the object, the epistemic neural network, in addition to taking S as an input, takes as an input a random index Z drawn from a reference distribution, which we take to be normal. And for each draw from the reference distribution, you get a different function from S to value. Right? And the idea is that if you look at the distribution of functions you get by sampling Z from this normal distribution, that represents your epistemic uncertainty about what this mapping should be. So for example, when used in the DQN context, you can use algorithms along the lines of backpropagation, but instead of just tracking a point estimate of a value function, you track a distribution over value functions. And that helps the agent reason about what it knows or it doesn't know. All right, so I just discussed this DQN example, but again, it was actually quite simple to modify DQN to do this. And as an example, one sort of epistemic neural network is what's called a deep ensemble. And what happens there is instead of learning one neural network, you learn K neural networks that are diversified through the training procedure. And they sort of behave like a particle filter where the K neural networks together sort of represent a distribution of what the function ought to be. Okay. So that's about uncertainty representation. And uncertainty representation is really at the heart of data efficiency because the agent needs to figure out what it knows and what it doesn't know if it wants to be data efficient. Now, I want to transition to think now about the role of information, which really helps us think about how to quantify our uncertainty and reduce that uncertainty using computational tricks similar to what are already developed in this reinforcement learning agent design world. Okay, so in order to think about information here, I think a couple of concepts are important. One is an environment proxy. So an issue is that, we want to apply agents to very complex environments where, if the agent retains all information it ever sees, it's just going to get overloaded somehow. There's just too much information. You don't want the agent to sort of store and process every bit it's seen from every pixelated image. At some level, the issue here is that the entropy of the environment could be infinite, or at least is way too big for the agent to store and access. And so an intelligent agent needs a way to prioritize which bits to retain as it learns. Okay, and the environment proxy is really a concept developed to organize the agent's thoughts on this. But environment proxy E tilde is just some random variable that is correlated with the environment, but requires far fewer bits to represent. And the idea with the environment proxy is it's sort of a filter. It says, as I take actions and register observations, instead of storing all the new bits that they present, I only store bits that tell me something about the environment proxy, right? So I don't store all the bits that tell me something about the environment. I only store bits that tell me something about the environment proxy. And actually, there's plenty of this going on in the reinforcement learning agent design world already. And DQN itself is an example of this, right? In DQN, instead of trying to learn a model that tells me everything about the environment, DQN learns an action value function. And then the action value function says, I don't really care about everything I'm observing. Let me just pick up bits of information from rewards and calibrate to rewards, right? So DQN learns a mapping that tries to predict reward, and it only calibrates outputs to rewards. and tries to learn from that. So in a sense, it's saying, I'm not going to pay attention to everything coming in. I'm just going to focus on rewards. But as we said, it's kind of silly just to learn from rewards. So the agent design folks have also introduced this concept called the general value function. And the idea with GVFs is to endow an agent an ability to learn from a portfolio of things that you want the agent to be able to predict and calibrate its predictions to. And so the idea with the GVF is, in addition to reward, you might define a set of cumulants, so-called cumulants. The cumulants are like rewards, but they're not rewards because they're not what the agent trying to optimize. They're just things that you're saying, the agent should learn to predict and calibrate predictions to. So by having cumulants in addition to rewards and trying to learn from cumulants, you're sort of redefining the proxy. Instead of a value function, it's a set of GVFs. And for example, some people tried this with the game of Miss Pac-Man, the arcade game Miss Pac-Man, where instead of having an agent that just predicts rewards, the agent predicts lots of simple things like whether it's going to get a particular puck, whether it's going to get eaten by a particular ghost. So with lots of these predictions, I think thousands of predictions, maybe 10,000 predictions or so, by trying to calibrate all these predictions rather than just rewards, a DQN style agent got 1,000x speed up in how quickly it learns to do well in Miss Pac-Man. Okay, so clearly this area of proxy design, of how to design a proxy where you're picking up enough bits and the right bits, but not all the bits because that's too much, is a really important topic that deserves more thought, but clearly that has a huge impact on data efficiency and reinforcement learning. And in the picture here, it's easy to simulate simple examples, which is what we did here, showing that as you increase the number of general value functions in a problem, the time it takes to learn to do well at something can go down dramatically. Okay. Okay, another important concept for data efficient reinforcement learning is that of the learning target. Now, the proxy is telling us how much information the agent ought to, or what information the agent ought to retain. A learning target tells us what information an agent ought to seek. Right? Now there are different things. And the idea with the learning target is that learning the optimal policy requires too much information. You may end up having to go around picking up too much information. And it's often better to settle for a simpler target. The notion I use for target is chi. And so pi chi is a policy that the agent might be trying to learn based on targeting particular information chi. And the idea is hopefully it's a pretty good policy, but one that requires far fewer bits of information than an optimal policy. And what we see is it's easy to run simulations where you show that by allowing for some loss relative to an optimal policy, you can dramatically reduce the number of bits the agent has to acquire, right, in order to do well. And by designing agents that explicitly take this into account, you can attain much lower regret over any reasonable time frame by saying that the agent's not going to target learning everything it needs to know to get an optimal policy. All right. So in order to reason about these sorts of concepts, as well as additional things, we've developed this framework for cost-benefit analysis, and the hope is that this can offer some practical insight that helps us understand tricks that agent designers are currently using and how to improve them. And this framework is really centered around a regret bound. So we have this regret bound that applies to all agents in all environments and takes this form here. And there's a few terms in this regret bound. One is the entropy of the learning target. So this is basically measuring how many bits I have to learn if I will learn everything that I'm seeking to learn. Then there's this target regret. That's the loss that I've resigned to booking because I'm going to try to learn a target policy rather than an optimal policy. And then really the centerpiece of this compound is what I call the information ratio. And the information ratio is this important link between reinforcement learning and this notion of information. And it really is representing this notion of a cost per bit of information retained by the agent. And it's where the agent's action selection policy comes into play, right? The agent's action selection does not influence the entropy of the target. It doesn't impact the target regret, but it impacts this information ratio. And the whole literature that's been growing over the past decade on this concept of the information ratio, and that's a very elegant and intriguing literature in its own right. But I don't have much time to talk about that today. But the literature has to do with understanding information ratios for various environments and agents. Also, the information ratio inspires a particular strategy for an agent's action selection as the agent tries to seek out the target information. It's called information-directed sampling. And this has been a very interesting area too, because it solves a number of exploration problems that previously were not addressed by other heuristics people had considered for exploration. But what is information-directed sampling? Information-directed sampling is an approach that aims to minimize the information ratio. So basically, at each time the agent tries to select an action based on an objective that would minimize its immediate information ratio. All right, so I hope this gives you a high-level picture of what we're trying to do here. And the broad point is that I think data efficiency really calls for some careful accounting of uncertainty in information. And if you'd like to get more into this, I recommend this paper that on this topic. And let me close with a fun simulation. This is the same cart pole problem where the agent is learning from 100 simultaneous instances of cart pole. And so it's distributing the way it explores so it can gather a lot of information much faster because it has 100 parallel systems it's controlling. And this agent within about 20 to 30 seconds learns to balance the pole in spite of the sparse reward structure. And this gives me hope that we can do something interesting in terms of data efficient RL. Okay, thank you.
I don't know if Shankar is still online. Okay, maybe I'll ask a question while we wait for Shankar to turn on the video. This was a great talk, Ben. Thank you very much. I just had a question. So you may have seen this line of work that maybe the first paper might have been by Chi Jin and Michael Jordan and Sebastian Bubeck, maybe, where they basically add like a UCB bonus to the value function. And they say that the regret in that setting is near optimal or something like that. So basically, instead of looking at information-directed sampling, they're just simply adding a exploration bonus. I was just trying to understand if there's a connection between. I mean, is that somehow directing you towards the right regions of the state space to explore? I guess basically the idea is that in the inverted pendulum type of example that you gave, I would think that what that is doing is that it's sort of, because certain states are not explored, you're adding a large bonus, and so your pendulum is sort of, our cart pole is sort of forced to move to those places. You seek those kind of places a little bit more. Is that the right intuition, or do you think you can do more using sort of information theory, or trying to look at some kind of mutual information to maximize?
Good. So first of all, this cart pole problem can be solved by that kind of an algorithm.
Okay.
So in a sense, it's not a good example of the benefits of information. It was more just to give you a sense of RL. But algorithms like UCB and Thompson sampling are only when the term optimal is sloshed around in this literature a lot, but it's kind of vacuous, right? But by the way, we've written a paper following on to them that builds on that work. And I like that work a lot. And so I like that area a lot too. And we wrote a paper that extends that to this kind of general RL setup, where it's not a finite horizon MDP, but this general environment, right, that goes on forever, and where you have arbitrary history dependence. So it's not that I don't like that line of work, I do, and we built on that. But things like optimism and Thompson sampling or UCB or whatever are severely limited approaches to exploration. Right? First of all, exploration was only one issue I talked about. Right? There were multiple issues having to do with information here, like what information you retain, et cetera. Like that algorithm, first of all, it's only learning from rewards. It's throwing everything else away. So it can't be optimal, right? But then you might say, gosh, is the exploration at least good? And the answer to that is no, right? And the issue is optimism is a pretty bad approach to exploration because it only ever selects actions that the agent thinks might be optimal. Okay. So suppose, and suppose, suppose you want to learn how to, use a new piece of software, right? So you can open up the software and do your first guess at what might be optimal. If that doesn't work, you do your second guess at what may, et cetera. That's UCB. Okay. There's nothing in there that says you're going to go look at the manual or Stack Overflow or something, because maybe that'll instantly tell you what to do. Okay. UCB cannot do that. UCB is try the action that you think is optimal right now. Okay. And so when you consider sophisticated environments where you start learning about information structures over time and then want to leverage that knowledge, things like Thompson sampling, UCB, optimism, those things all are horrendously bad, right? And so that's where this more nuanced understanding of information comes in.
Ben, thank you. That was a wonderful talk. Hey, so certainly, from these work and data controls to understand.
I'm sorry, Shankar, I cannot hear you very well. There's like an echo.
What remains to be learned has certainly been a theme. But what makes you think that sort of using these information theoretic bounds, which are at best non-semantic, why would they be good ways of really trying to understand? So the question of the cart pole, you're trying to learn something about the dynamics. There's multiple agents. You're trying to, okay, I can understand for the bandit problem, your comments. But why do you think that these old notions of entropy are the right ways of measuring what you've learned?
Good. So I don't know that this is the best way, and I can't claim that. In fact, when I talk to my information theorist friends, they like to say, hey, we developed this stuff for communications. It's going to be a pretty big coincidence if this is the right thing for reinforcement learning, right? And I understand that sentiment. And on the other hand, there's all these super interesting tricks that people have developed over the years in reinforcement learning that they don't understand and that they don't understand how to improve. And I got into this about over 10 years ago when I just felt like we're hitting a brick wall just using linear algebra and concentration inequalities. And then I started exploring information theory and like, wow, I can do a lot more using information theory than what I could do before. So, the approach is more like, how do I take a few more steps than what we could do before? Not how do I make sure that this is the, bottom line and final word on reinforcement learning.
Thank you. Please, I think the paper that you referenced in the end is really a wonderful pièce de résistance. And as we were listening to you, we thought, boy, and I want to plug this to everybody who's still listening, to really study your paper, because it's really a fantastic compendium of wonderful results. So, Ben, it's very nice to see you. And I agree with your explanation about, so, the information theorists here too, they say, we never did it to control dynamic systems, we did understand games, to understand human machine interactions. But on the other hand, the psychologists and, your colleague, for instance, Mr. Noah Goodman, they say, they're incredibly simple models that you can use for humans interacting with machines. And you, in fact, be my guest and try them. And so it might be that these entropy measures are good enough. So, as a sort of bottom line. So, anyhow, very stimulating.
Well, one thing intuitively that I've sort of found is in a lot of the design of these tricks in reinforcement learning, right, there's some intuition underlying them, right? That they're not designed to solve the Bayesian reinforcement learning problem, right? They're designed based on some other heuristics. And one thing that I find is these heuristics are sort of aligned with information theoretic thinking and concepts. And so in the sense of understanding what's going on and how to improve it, this seemed like a good roadmap to me. Now, my information theorist friends complain because their perspective is, you should only do something if it's going to end up with matching upper and lower bounds. But the reinforcement learning perspective is what we're trying to do is so complex that anything that takes us a step further is worth doing.
By the way, Ben, there's a question from Max Draginsky. I don't know if you want to answer.
Yeah, please. Go ahead, Shrikant. We have some AV issues. That's why you're getting an echo. So why don't you?
Okay, I'll just read it out for everybody. Regarding computation first, information later, there's the well-known Moravec's paradox in AI/robotics that says roughly that the complexity of any computation by an intelligent agent is nothing in comparison to sensory motor control. This will be the big part of interacting with the environment. Any comments on this, especially given that there's quite a bit of work connecting information theory to control?
Okay, so it says, I'm intimidated because it says well-known and I don't know this.
Yeah, me neither. I don't know this either.
But I'm trying to parse the question. Complexity of any computation by an intelligent agent is nothing in comparison to sensory.
Perhaps he's saying that control is somehow much more complicated than the computation. I don't exactly, I don't know, Max, if you're still there, maybe you can expand on it, or.
That'd be great, because I'm not even sure how to parse the sentence, actually.
Yeah, I'm not sure either, so. Okay, maybe we can skip it, but then maybe, I mean, you know Max well, so I'm sure you can.
Can Max talk on here, or?
I don't think so. I think that's one
Ah.
problem with this format. Yeah.
Could
That's
unmute
what
Max
Mark
if you'd
said.
like.
Yeah.
You can type a comment. Maxim, do you have some elaboration of your question? I also am having trouble fully understanding the question.
I don't know if we can. Yeah, maybe we should skip it and then, have Ben and Max talk to each other. Sound good? So maybe Shankar, we can wrap up.
Sorry, we have moved into some new digs, so we're still getting used to the new AV. I apologize for all our travails here, but Ben, that's a fantastic talk. We look forward to studying your paper in greater detail. I think we'll have to find out about Moravec's paradox offline. Thank you, Maxim. I'm sorry we couldn't elaborate on the question. So Ben, as always, you are a wonderful speaker. Thank you very much for speaking. So thank you all.
Thank you very much for
everybody.
having me.
Have a good afternoon.
Thank you. Bye, guys.